I'll start off first half or so slides, and Chuck will finish up. What we decided to do in this overview of SNIA Emerald Spec 3.0.1 was to combine content I had as well as what Chuck had. Chuck had some information which was more what is being tested and why, which was listed initially in the agenda as a presentation a few sessions from here, but we just put the two together because we had overlapping stuff. So the intent here is basically give a fairly high-level overview of what's in the new spec, the 3.0.0.1. And we made it a point not to go back into the previous too much, other than a few points where we do some, compare and contrast. So it's mostly just highlighting what's new and what's different in 3.0.1. So this is straight from the Emerald spec. This is the abstract.
Herb, this is Wayne.
Yes.
Just a brief interruption. If you could go to the bottom right of your screen and go into presentation mode, that's just a little bit to the, yep, that one. There you go, slideshow mode. Yep.
Sure.
That will provide a larger picture for everyone. Thank you.
You bet. Yep. So as I mentioned, this is straight from the abstract. What the Emerald spec is. It's a power efficiency measurement spec. Power efficiency, which the metrics of which combine both the performance and the power into what we're calling a power efficiency. And it's a measure by which energy consumption efficiency of storage products can be measured. And of course, the end purpose right now is to supplement and support Energy Star in this measurement technique. There's a number of specs already that have been released. They're all available. If you go to the emerald.org site, they're all available there for download, and it's listed here too as a handy point. Here's the history of the Emerald spec itself. The release, the date, and I just identified some of the key changes. All of them had, a fair amount of editorial clarity upgrades as well, but what I've identified here in the right column are the key changes. So the first version came out quite some time ago, August of 2011, and that was the initial release. We call it the SNIA technical position at that time, and for several releases after, it included only block storage. The second release, version 2.0.2, came out a couple years later, and there we added some definitions of the hot band workload and some auto tiering, and we changed some response times and revised the VD bench scripts used for block storage. The current, I guess it is still the current version. It's no longer the current. It's now been supplemented by the 3.0.1. But up to now, it's been version 2.1.1. That was in effect for quite a while. It came out in 2015. Where we just made a few minor changes to the previous, where we specified some test data sets and revised some test steps for the comms themselves. So this spec, the current one, 3.0.1, came out summer of last year, and there are a fair amount of changes made to it, or additions made to it. We added tests for file access devices of online and near online taxonomy categories. That is the one and biggest change. We eliminated some tests for parity rate as a comp. We improved tests for data dedupe and compression comps. We eliminated some taxonomy categories, adjunct product, interconnect element. They really weren't being used. We added a stable storage definition. We tried to align the power requirements between our spec and the Energy Star spec. And we added some temperature meters to annex to the appendix. And the appendix actually grew quite a bit. And just as a note, we're planning to submit an ISO version of this spec, of the version 3.0.1, to ISO by summer of this year. That's just submittal to them. The review and approval process by ISO takes quite a while. Could be up to a year and a half. So, we want to get it in there as quick as we can. And we've already made some good progress on getting this version, this 3.0.1, reformatted into an ISO type document. And just verbally, and it was mentioned by the Energy Star folks, besides submitting or trying to get an ISO version of 3.0.1, we're getting our ducks in a row for the next Emerald spec, which is version 4.0. But that'll take us all this year to create a initial draft of it. Maybe we'll have it by the end of the year or early next year. That will have a brand new taxonomy and perhaps some new workflows, a number of different things. The new taxonomy is something that's front and center in our thinking right now, and we'll probably come up with some form of white paper for the taxonomy, the new taxonomy itself, which we'll send out to industry to stimulate some conversation and feedback, things like that. Okay, moving on. Here again is another type of highlight of Emerald version 3.0.1. It's a major extension of the previous one. So what we've done is we added the test methodology for the file access storage devices. It's based on an existing spec SFS 2014 benchmark. So we've substantially expanded the range of the different types of testable storage devices. It does retain all the major elements of the previous spec, including the storage taxonomy, the block I/O test methodology. And as was identified by Energy Star folks, that this Emerald spec version 3.0.1 is what's being referenced in their new version 1.1 to include file access devices. For those folks that haven't looked at the the Emerald spec yet, this is just an overview of the different clauses in it. It's grown to about 83 pages. There's a lot of meat. There's a lot of content in it. Each time we came up with a new spec, it grew some more, and now we're up to 83 pages. So there's quite a lot of stuff in it. But really, all we want to do here is just identify what's new and changed from the 2.1, and that includes some things in definitions, a few things in taxonomy, a little bit in comms, and the majority of it is the test definition, execution rules, and metrics associated with the file access I/O. So, first item that we made sure to add was the definition of stable storage. It became apparent to us when we were looking at the spec, SFS spec, because it was in there, and we thought, wow, if it's in there, we really need to make sure it's also included in the Emerald spec relative to all types of storage, not just file, but like the block too. And what it is just a definition that for storage that retains its contents over power failures. We also put a more complete definition of it into the Appendix C, where we basically identify that that stable storage is a type of storage that retains data for a minimum of 72 hours without external power in case of these items down here: repeated power failures, hardware failures, or software crashes. And in the taxonomy itself, we made it a required attribute of online through online 6. Now the taxonomy itself, this will be covered in a little bit more detail later on today, but as a highlight, these are the types of categories: online, near online, removable media, and virtual media. Of course, what we're most interested in is online. Those are the eligible categories in the Energy Star spec, and here are listed just several of the attributes of the categories: access pattern, max time to data. There's considerably more attributes in the individual categories themselves when you look at the tables, and we'll highlight those in the when we cover taxonomy later today. But just to point out, block and file, they fall under online and near online categories. Of course, again, we're interested in online 3 through 5. Because, again, those are the eligible Energy Star categories. What we've done is remove the several categories, adjunct product, the interconnect element. That's a change from the previous spec. They just simply weren't relevant, weren't being used at all. So we got rid of them. And we also removed the attribute which we call accessible data, because the only categories that did not have to have accessible data were the adjunct product interconnect element. So boom, it disappeared. So that also was a change from version 2.1.1. Oops, went wrong. Excuse me. Okay, comms. This was covered yesterday in detail by, I believe, Carlos. Yes. And just to highlight again, there are techniques that reduce the consumption of space required to store a data set. Here's the 5 different comms that have been defined. In the Emerald spec, we define simply qualitative heuristics. They're simple pass-fail tests. They're intended to verify the existence, the presence and activation of that particular comm. And they are applied to both block and now file access in a similar fashion. What we did change from version 2.1.1 is for parity RAID, we eliminated the presence tests. They're no longer defined for parity RAID. Parity RAID is actually a requirement by Energy Star for online storage that it does need to have parity RAID. Okay, and I think that's my part of this presentation, and the rest Chuck will cover, where it jumps in more detail on the actual testing of the block and the file, particularly the file. So Chuck, are you there?
I'm here.
Great. Have at it, please.
Okay, so I'll ask you to do the page turning if you don't mind, because I think
Yes.
you got control.
Yep.
Okay. So yeah, as Herb alluded to, we significantly changed the workloads that are part of the mix now on the file-based side, and they're enumerated there in the on the slide that's currently showing. There's 4 workloads that we've adopted from the spec SFS 2014 suite: VDI, a database. VDA, which is a video acquisition application, a database workload, a virtual desktop workload, which is essentially where we virtualize a bunch of desktops and so forth, and populate it with a very busy worker environment. And then there's a software build that's there at the bottom of the slide. So those are the 4 workloads that we've adopted from the spec SFS 14 and included them into version 3.0. So next slide, please.
Actually, I have a question.
Okay.
About, so the latest version of spec SFS 2014 SP2 actually includes 5 workloads. There's an additional new one called EDA, and I'm not seeing it here.
It is not.
Okay. Is there like do we have to run a specific version of the spec SFS?
No. The 4 workloads that are enumerated here are the ones that are currently in scope for the Emerald specification. We anticipate, and you've seen the first instance of it, of additional workloads being added over time that we may or may not adopt in the Emerald environment, depending upon the value add. That was one of the benefits that we got by hooking our wagon to the Spec SFS 2014 star in terms of the workload evolution. And maybe version 4.0, probably not, maybe even further beyond that, that any of those workloads that we deem, acceptable, we'll go ahead and include those. But for right now, it's just these 4.
Okay, so regardless of what version of the tool we're going to use, it's just we just need to cover these 4 workloads.
Yes, that's correct.
Okay, thank you.
You're welcome. Next slide, please. And we mentioned early on that one of the sessions that we're combining here is the what's tested set of parameters and so forth. And what you see here is a contrast and compare between the file access workloads, which we've included here only for reference, and juxtaposed is the file access workloads that are there on the right-hand side of the slide. Again, in the past, we had 5 workloads that we ran for block access measurement, and today on the file access side, we have 4. You'll also see, if you look at the details there, that the actual measurements that are made between these 2 are different also. In the small block random workloads on the file access side, we measured the I/O rate, or IOs per second, per watt. For the small block workloads, which is the hot band, random reads, random writes, and the sequential workloads you'll see were measured in terms of millibytes per second per watt. Okay? If you take a look at the file access workload description, they're all being measured in terms of millibytes per second per watt. And I'll also go into a little bit of detail about why we've chosen that and exactly where those measurements are coming from. Questions?
Yes. So for Emerald 2.1.1, we run only the block access workloads, and so does that mean that for version 3.0.1, it's required to run both of the block access workload and the file access workload?
I do not believe today, and folks correct me if I'm wrong here, that it's a requirement to run both. The idea behind including both in the spec is to be more inclusive in the product mix. We can still run, and correct me if I'm wrong, a block access only workload using 3.0 and just report it as such.
Correct, yes.
And or we can run only file access and report it as such. It's not a requirement that they both be run.
Okay. So we can do either or both?
Yes. Yes.
Thank you.
And you'll probably want to pick the one that gives you the best sweet spot. We can go into that in a little bit of detail later on. But so anyhow, this is to contrast and compare the workloads and what's actually being measured in association with those workloads. Again, it's IOPS on the block side, and it's all millibytes per second on the file access workload side. Next slide, please. Here we see a little bit more detail about some of the file access workloads. As we mentioned, there are 4 of these workloads, and every good benchmark has to have some sort of a throttle associated with it. And in the case of the Spec SFS workloads, the business metrics actually represent the load parameter. For example, in databases, the throttle is the number of databases that you are exposing the storage to. For the software build, it's the number of builds. It's a degree of parallelism, if you will. For VDA, it's streams, and for VDI, it's desktops. And you'll also note there, and this is taken out of the spec, for those readers who are interested, the spec has excruciating details on the content of these workloads and the business metric application to those workloads. Here you see at least 10 uniformly spaced business metric workloads shall be specified for a valid test execution. That's taken right out of the spec SFS 14 specification. You also see here enumerated at the bottom a little bit of a hint in terms of what the storage requirements are going to be. Per database, it's 24 gigs. Software build is 5. VDA is 24. VDI is 12. And again, you multiply these times those metric workloads that are cited in the table above to determine how much storage space you're going to need for your particular submission. This is kind of handy because if you think about the way we did it with file access, you all pretty much got to pick whatever quantity, whatever capacity you wanted. This is a little bit more strictly defined because one of the problems that we were having here is a way to scale the amount of space required for a given submission based on its main metrics. In this case, it would be megabytes per second. Here we kind of get it for free because it's actually built into the spec SFS 14 specification. Questions? Next slide, please. Here we enumerate the steps in the test execution process. And for those who are familiar with block access, there's no news here. There's a prefill that puts the correct data patterns, and that's important when we talk about future expansion into 4.0 because the data patterns are one of the things that are going to allow us to use the COM data as part of the actual metrics. There's a conditioning test which actually ensures that we have steady state operation before we actually do the test measurements that are part of the active test, bullet number 3. Then there's a ready idle test that's done, and the idea behind the ready idle is to examine the storage, its behavior when there is no applied host I/O. Idle's kind of funny because of the housekeeping that's necessary or that's provided as a feature, if you will, on some of these devices. It turns out that idle can actually be busier than busy, depending upon the housekeeping activity that's being applied there during the slack periods. And then we have capacity optimization tests, if it's defined for that particular product. To contrast that, we have the execution of the 4 workloads that we've already cited. You'll see that there is an instance of a ready idle test there also, which is the basis of that ready idle metric. And essentially, those ready idle tests in those 2 environments they're identical. And then we have a capacity optimization test. Again, today, those 2 last tests are identical. We may find that down the road we're going to have to do some bifurcation in the test process there, but for today they're both identical. So, okay, questions? Next slide, please. We're going to talk briefly about measurement boundaries, and let me explain kind of a little bit of background as far as why these 2 test environments have different measurement boundaries. When we measure the degree of activity, i.e. the IOPS and the megabytes per second in the block environment, these IOs are by definition what's considered DIO, direct IO. They're not buffered in the IO stack that goes from application space out to the storage. As a result, what we see from application space is what the storage device actually sees. There may be some minor driver interaction that occurs there, but for the most part, if you see 10 IOs from application space, your storage device sees 10 IOs. That's considerably different in the file access environment, can be considerably different in the file access environment, depending upon how the parameters that you use when you set up the files, when you open them up and so forth for access. May turn out that you're getting some assistance along the way from buffer caches and so forth that are in the server that represents the client. And from application space, the observed response time as a result may not really have anything to do with the storage subsystem. For these reasons, what we're doing is we're measuring the amount of work that's being done by the file access workload at a different point in the architecture, the test harness, if you will, than is measured by the block access, which all comes out of the workload generator that resides in application space. So at the last bullet there is a hint as far as where we're deriving these I/O metrics from. It's from either the network driver on the server itself or from the interconnecting internet protocol switch. We'll go into a little detail here in terms of a schematic in a second, but before we do that, any questions? The idea behind this is that we want to actually measure the real work that the storage device is executing. We don't want any inflated I/O rates and or reduced response times due to the caching that occurs between the application space and the actual storage device. Any questions? Next slide, please. As promised, here's a schematic depiction of these two environments. On the block access side, you see that the I/O driver details actually feed directly into the data collection system. We have the product under test and the I/O load driver produce the metrics, the actual IOPS, megabytes a second. There's also a temperature probe that is providing input into the data collection system in addition to the power meter. Now we contrast that to the diagram on the right that shows the file access test schematic, and here you'll see that partway down, about midway through that diagram, there's a couple of new pieces that have been added in there. We talked about this in the previous slide. One of the data collection points can be the network switch. The other data collection point can be the I/O drivers on the server itself. So there's a slight modification as to the measurement boundary for the actual real work that's being done. The rest of the schematic is pretty much the same. Any questions about that? Makes the environment a little more complicated, but it actually measures the real work that's done by the storage device, which is what we're trying to measure. Any comments or questions? Next slide, please. Again, in the vein of what's being tested, here are the data collection summaries that we have in terms of the block and the file access workload environments. Conditioning test, the active test, and the idle test on the block side. And here we have an initialization that's actually done on the file access side, a warm-up period, an active per load. Remember we talked about 10 different load points? There's an active per load measurement that's done there. And then last but not least, once we remove the I/O demand, there's a ready idle test that's done. Very similar to the ready idle test that we're doing on the block in the block environment. Any questions about the metrics or the interval, the sample intervals, or the durations? These durations, by the way, I should mention on the file side of the equation are all defined verbatim in the Spec SFS 2014 specification. We're just aligning our environment to what's spelled out there in that spec. There's no sense in reinventing things that have already been proven.
I have a question about the power meter collection interval.
Okay.
So I thought we were supposed to take the operations rate every 10 seconds and divide that by the power. But does that mean that we're going to take 6 different operations samples and divide them by the same power number? Because you're doing the operations every 10 seconds and the power meter every 60?
Yeah. So the idea behind that is that we wanted a sufficient number of data points so that we had something, and this a statistician would have a fit with this, that's approaching some sort of statistical stability. The idea behind cutting the operations interval into smaller pieces is to allow us to collect more of those data points. That combined with the fact that what we're trying to do here is to the power variability is going to be in general considerably less than some of the jitter and so forth that we may experience in the operations rate. So the idea there was twofold. First of all, to give us enough data points to actually do some math on, and secondarily to preserve as much of the original spec as we could in terms of the power meter sample window. So yeah, there's a little bit different math that's involved in that, and the idea was to create more data points than the original Spec SFS 2014 would allow. So.
Okay, so you're going to get, actually, the power meter you're going to average out every 60 seconds, and then for all of the 6 operations rate samples, you're going to divide that by the same wattage from that 160 seconds.
That's correct. That's right. That's right. Yeah, yeah.
Thank you.
You're welcome. Any other questions or comments before we move on? I think we're pretty close to the end here.
Yeah, that's the whole presentation. It's completed. So any questions are fine at this point. Okay, I think we're done with our presentation.
Thank you all for your attention. Appreciate it. Go ahead.
If you can just hold for a second in case anything's coming in on.
Yeah, it's a good call. Yeah.
If you're trying to ask a question, your line might be on mute. You'll find a red microphone with a slash through it off to the right side. Just a point, Chuck. You mentioned about it looks like you could be done with testing if you just looked at a table like in less than 2 hours, but that's not true because you're supposed to have several load points, and so if you're doing like say 10 load points on warm up and 10 load points on your active load, and you got to do the 4 workloads, you're actually into a day of testing, several hours of testing, and not 5 minutes plus 5 minutes plus 120 minutes. No.
Yeah, so okay. There is probably weeks involved in getting to this money run. So there's, and again, if you'll notice the init test duration isn't spelled out there. It says NA. That means it's variable. There's an awful lot of work that's going to be required in terms of tuning we talked about the business metrics, the throttle, if you will, tuning that throttle to the particular configuration that you have. And of course, we talked about the dependency of the size of the working set on the magnitude of that throttle. There's an awful lot of behind the scenes testing and tuning that has to go on here. But in order for us to run through this test, it's not really all that time consuming, given the fact that we've got it pre-tuned ahead of time. And Don, Caps, feel free to add in comments and so forth here, because you have mountains more experience in this environment than I.
Yeah. So so what I'm trying to get at is, like, once you have your system all tuned, you know, whether that you lucked out on day 1 or you lucked out on day 31. Once you get to your system that you feel was tuned and you want to do what you're calling the money run, you know, what would that day look like in terms of how much time would be set aside? So I'm just trying to help everyone on the phone just gauge expectations that, you know, don't start a run at 4 o'clock in the afternoon because it won't be done until midnight and you can't go home while it's running. You should start it at 8 because it's going to at least be 6 hours and you want to be there to make sure it completes correctly.
I would like to defer that question, please, if you don't mind, to Don Caps.
I'm asking
okay, good. Thank you. Okay.
Yeah, I'm not looking for, maybe you have the answer, but I'm trying to maybe further articulate it so, you know, you got 20 people on the line that would love some more guidance so that they don't have disastrous days in front of them.
Okay, I got my mic turned on. This is Don Caps. You'll know from your tuning how long it takes. So to answer that right now without knowing the configuration of the system, the answer is undefined, because you don't know, just like on your pre-fill, how long does it take to fill an infinite size bucket? Well, infinity. Well, the same is true with any benchmark. If you have an initialization phase, a pre-fill phase, how long that pre-fill is going to take to actually initialize all your data set is dependent on your speed of your storage system. So it could be anywhere from a few seconds to, a few days, depending on how slow or how fast your storage system is. But during your tuning, when you're trying to, get this thing to be properly tuned to run the benchmark, you're definitely going to figure out how long the initialization phase takes. And it is usually 90% or 99% of the time that you'll spend is during the initialization phase. The actual run is 10 minutes per load point times 10 load points is 100 minutes, so under 2 hours. But the initialization phase is what can take the time.
Okay, so you need to be running these all through a sequence and not take a break and do something else. And with the system, it needs to go from, as we look at the table, top to bottom, as you complete.
Well, you want to do your 10 load points in sequence for each workload type. Don't stop. You do your 10 load points. That'll keep your data set fresh, and you'll be able to reuse the previous load points data set and grow on it for the next load points data set. So you won't have to start from scratch every time. So you definitely want to do that. In between your workload types, you may want to remove all those files from the previous workload type because you're not going to use them again, and you might want the free space back, and that's fine.
And in that table, that table is for one workload, and
right.
You've got to do 4 workload types.
Yep, correct. Yep, that's why I just wanted to. I know the next 3-day session that we run, we'll get into all these details, but I just thought at a high level for project management and lab scheduling and expectations, I was just trying to put some guardrails out there.
I guess the other thing is that when you have to do 4 workload types, but I think you only have to do ready idle once.
Yes.
Correct, Don?
Yes, that's correct.
So once you've done one workload and a ready idle, then you just need to do the next set of workloads, which, as Don said, could be about 100 minutes once you get it set up. But you don't have to do ready idle each time. One set of ready idle is all that's required.
Okay, that was meant to be an icebreaker question for others. All right. Going once, going twice on the questions front.
You know, and the same scenario applies on the block size. I mean, if you merely total up the numbers that are in that table and say, this is how long I'm going to need that system for, you will be woefully disappointed.
Yeah.
One quick question. The power meter 60-second collection interval, is that a change from the older specification?
I don't believe so.
Okay. And we allowed to have actually a finer interval, right? Like smaller than 60 seconds? Or is that a hard requirement?
Well, so the data reduction tools in the block environment pretty much rely on that collection interval because there's some alignment that's done between the I/O rate and the megabytes per second VD bench output and the output from the power meter. So there's some dependencies on that data reduction tool that interval be as is stated in the table here. Can you use a finer grain and then somehow average it? I would suspect that would involve a little invention from a data reduction tool standpoint, because if I recall, the data reduction tool on the block size pretty much requires that these intervals be as stated here.
Yeah, when you mention data reduction tool, and it sounds to me that you have more data than you need, and then you reduce it to 60-second interval, and then like kind of sampling the data that you have, like reduce it to get a reporting per minute. But anyway, I mean, I just want to know if this is a requirement, that's fine. Then, I mean, it just wondering.
This is Samuel. This is just a comment. I believe the data reduction tool, as Chuck said, is because when you run the test for 40 minutes, you only use the last 30 minutes of the run for your actual calculation. So that might be why you have the data reduction.
I see. Okay.
Yes. And also, Chuck, one quick question. If we're testing for both block and file access storage unit for Energy Star purposes, are we supposed to use the same configuration?
Absolutely not.
Okay.
And the reason that I'm so quick to reply to that is these workloads are so very different.
They're different. Okay.
Yes.
All right. Thank you.
These can actually be treated mostly autonomously. We don't require any trans test data configuration consistency. You can set up the sweet spots in these two environments totally differently.
Okay. And that's what I thought. Thank you.
Mm-hmm.
I thought we were required to take the power measurement a minimum, well, at least every 5 seconds. And so we've always been taking the power and then averaging it out over, all 60 measurements to get a minute's worth. And that's...
Yeah, you all have you have a custom tool, if I recall.
Yes, and I thought we were doing that because it was required. If you could offer some clarification on section 7.2.9 of the spec, where it says power and voltage measurement shall be recorded to durable media using a period of not more than 5 seconds.
So in terms of the data reduction, when we actually get into doing these calculations, I believe that and I could be wrong here. Some of my data here is pretty old. I believe that what we're using is the 60-second interval for that power measurement. I don't believe, and there was some controversy. We went back and forth on this, and you guys were involved in. Is this DeMarc?
Yes.
Yeah, you guys were involved in this as it evolved. So it may turn out that some of the older versions of that spec do in fact have differences in the actual power sample. That the sample interval that's actually recorded by the power meter.
Chuck, this is Dave Teal. I believe I think this is an area where there was a change made between V2 and V3.
Okay. Thank you. In which case, then, your past experience would indicate a different sample interval than what's cited here in the table.
Yeah, I'm looking at the current spec, and it's saying 5 seconds. So I was just wondering, not on the table, but at an earlier section at 7.2.9. So that's why I was asking for clarification.
Mm-hmm.
Yeah, I've also seen that, and I think, like Dave said, it was a change that was made from previous sections, and I don't think that section was effectively addressed. So there is still some confusion there, but we've always gone by the 60-minute recording period.
Okay.
So we don't do 5 seconds in average. We just go by the 60 because that's what PD Bench does with the data. So
right. The idea there was to line up those timestamps.
Okay. So then we don't have to follow that 5 second thing that's elsewhere. Got it.
I was wondering that, Dave and the technical team, if you just want to look at that offline, and then we come back as part of this training series to just be certain of our answer.
Yeah, we can do that. We can do that later on in one of the subsequent sessions. But I'm starting to recall some of the details. It's kind of scary. You set the power meter up to measure every 5 seconds. But if I recall, I think that thing writes to that file every minute.
Well, Chuck, there may be a discrepancy between two parts of the 3.0.1 spec.
Yeah.
I would suggest that we take that to the twig and, if possible, before the training is over, but whenever, and then get back to people.
Yep. So you have it captured well, Dave?
Yes, I do.
Okay, good. Okay. Other good questions or noted discrepancies? All right. Not hearing any.
Isn't that part of your data reduction issue as well? If you've got more samples of power than you have samples of data rate?
Yes.
That's part of the data reduction as well.
So Don, part of that, again, I'd like to dig into the gross details before we make any kind of commitment here, but it seems to me the power meter's collecting stuff a whole lot more frequent than that file's being written to. And when you write that data to that file, it's averaging those power measurements over the timestamp between the file entry it's writing now and the previous one that it did. So there's some averaging that's going on even outside of the data reduction tool.
Okay.
And that was one of the, well, without going into too much past history, that was one of the challenges of the data reduction tool, was to line up the time samples okay? And then once they were aligned, there was, if we have different measurement intervals as far as where those recordings occur, then there's another alignment that has to occur in real time. I think that we were able to eliminate one of those by adjusting these collection intervals. We'll investigate that and get back to folks on one of the subsequent sessions.